Alright, so today we're going to be talking about finding intervals and radii of convergence for our arbitrary series. So over the last few videos, we've been sort of slowly building up the machinery to finally tackle this challenging problem. One of those things that we have kind of looked at before, and I'm going to briefly cover in order to introduce this concept, is the convergence theorem. Convergence theorem for power series, which, to summarize, essentially states that a power series either converges, well, there's three cases of convergence, three cases for convergence intervals in a power series. Either the first case is we converge on some interval x minus a is less than r, and endpoints where x minus a is equal to r, so the absolute value of x minus a is equal to r, may or may not converge. The second case is we converge for all x, and the final case is we only converge at x is equal to a. And this a is essentially for when we have a power series that looks like the sum of from n is equal to 0 to infinity of some constant at n times x minus a to the power of n. So it's a power series centered at a. So the three cases that determine the different intervals of convergence that we can have in a power series is either we converge at all r, in which case the radius is infinite, and here the radius is 0 when we only converge at the center, and then over here our radius is r, and our interval we have convergence at all the values inside of the interval, and the endpoints at which x minus a is perfect, or the absolute value of x minus a is perfectly equal to r, they may or may not converge. So to find out the exact interval and to find out whether the endpoints converge or not, we have to specially test the endpoints itself. So that's what the convergence theorem told us, and if you want to get to know more about that, I previously covered it. And we also learned about a whole lot of tests, that help determine divergence, absolute convergence, and conditional convergence. So given all of this machinery that we have, specifically the fact that we know some properties about how power series converge, and secondly, we know how to test for convergence of random series, we can now use these two in tandem to determine the interval at which a power series will converge, and also determine the radius of its convergence. And so let's just do a lot of problems relating to us needing to find out these properties. So let's just get into it. The first problem is, so all of these problems is find values for x where the given series converges. And so the first series that we're worried about is the sum from n is equal to 1 to infinity of -1 to the power of n plus 1 times x to the power of 2n divided by 2n. And so the first thing that you probably want to do is when you see a series is to kind of understand the behavior for small n. So for small n, it's going to be the first term when n is equal to 1 is x squared divided by 2. Then you have a negative term since you have this negative 1. And then that's x to the power 4 divided by 4 plus x to the power 6 divided by 6, and so on. So we see it's an alternate series. And we also see that our denominator is increasing as our terms increase. And we also see that the power increases, right? And so the first thing that we need to the first thing that we absolutely need for a arbitrary series to converge is that the limit as you know n tends to infinity of x to the power of 2n divided by 2n heads to 0. And that only happens when x is between 1 and negative 1. Um, actually, that's not the case here. Oh wait, never mind. But the fact that we need the fact that we need our series as the nth term, as we head towards the nth term of the series and n tends towards infinity, we need the limit to go to 0. That comes from the nth term test. So we need that to be true. And the first thing that, the first way to approach this is, let's try to find a test that we can use to find an interval of convergence. And then we can kind of check the endpoints if they exist. So one test that seems most reasonable in this case is using the ratio test. So the ratio test tells us that the limit as n tends towards infinity of u of n plus 1 divided by u of n. So that's what we're checking, and that's essentially the limit as n tends towards infinity of x to the 2n plus 2 divided by 2n plus 2 divided by x to the 2n divided by 2n. And that's the limit. And notice how I'm ignoring this negative 1 term, because this ratio test is a test of absolute convergence. So at the insides of any interval, of any convergence interval, we're gonna have absolute convergence, and only at the endpoints can we have conditional convergence, and that's why we can kind of use this and only check for conditional convergence at the endpoints. But going back to this limit evaluates to x to the 2n plus 2 times 2n divided by 2n plus 2 times x to the 2n. We can simplify this to limit as n tends towards infinity of 2n divided by 2n plus 2, and then we just have x squared. And clearly this x squared term is not dependent on n, and as n tends towards infinity, 2n divided by 2n plus 2 just tends to 1. So we essentially have 1 times x squared. So we tend to x squared. And our ratio test tells us that x squared must be less than 1 for convergence. Right? That's just a result of the ratio test. And solving for that, we get x is just less than 1 and greater than negative 1, because we're taking the square root of 1, and so we can have negative 1 and 1. So that's what the ratio test tells us. And so what we have is we have this interval of convergence, and because this was a power series, we know that we have a finite radius of convergence, so we need to check for the endpoints because they can separately be convergent or not. So let's check for the endpoints, and here the endpoints are when x is equal to 1 and negative 1. So when x is equal to 1, our summation looks something like this: negative 1 to the n plus 1 divided by 2n, since 1 to the power of 2n is always 1. And so by the another way to rewrite this summation is 1/2 times the sum from n is equal to 1 to infinity of negative 1 to the n plus 1 divided by n. And this is just the harmonic series, which we know is conditionally convergent. And so we can say that at x is equal to 1, we converge because we're conditionally convergent by the alternate series test. And I skipped the fact that, I skipped explicitly applying the alternate series test because we've already applied it on a harmonic series. Now, when x is equal to negative 1, our summation, so this is x is equal to 1, and for x is equal to negative 1, we have the summation looks like from n is equal to 1 to infinity of negative 1 to the n plus 1 times negative 1 to the 2n divided by 2n. Now, negative 1 to the 2n will always remain 1 because you're always multiplying, or you're taking it to the power of an even term. So this is exactly going to simplify to our x is equal to 1 case. And so because we already claimed that when x is equal to 1, we're conditionally convergent, and when x is equal to negative 1, we simplified to the same case. When x is equal to negative 1, we're also conditionally convergent by the alternate series test. So finally, we know we're convergent at negative 1 and 1, so we're convergent at the endpoints, and we're also convergent everywhere in between. Therefore, interval of convergence is negative 1 to 1, and radius is 1. So note how the radius doesn't change whether or not our endpoints are convergent or not. So you can always get the radius right, even if you get the endpoints wrong, where the endpoints are something you have to specially test. So that was the first example. Let's move on to the next one. This time our series is the sum from n is equal to 0 to infinity of 10x to the power of n divided by n factorial. Now, like I said, we kind of first want to see what this looks like for small values of n. So this is equal to, when n is equal to 0, it's 1 divided by 1 squared, so 1 factorial, so it's just 1. Then you have 10x, then you have 100x squared divided by 2 factorial, and so on. Right? And so let's see one test that we can use to determine whether or not this is convergent or not. And one test that seems reasonable for this is also using the nth term test. All the other tests seem a bit more complicated because I can't find another function to use a ratio test, nor like a limit test. So the nth term test seems the best possible use. So a limit as n tends to infinity of u of n plus 1 divided by u of n. Same thing as the limit as n tends towards infinity of 10x to the power of n plus 1 divided by n plus 1 factorial. Now I'm going to simplify the step of like me previously writing the other fraction corresponding to this on the denominator, because I know what will end up is I'll get that n factorial over here, and I'll get the 10x to the power of n here, and that simply simplifies to the limit as n tends towards infinity of 10x divided by n plus 1. Now as n tends towards infinity, this term will be really, really big, and this term is just a constant. So this limit will tend towards 0. And so because of the fact that our limit tends towards 0, no matter what x value we have, and this is another power series, we simply converge for all x. And we know that this is a possible convergence pattern in a power series, so this seems like a reasonable answer. So that was an example of where we have a we have convergence on the whole domain, and the radius is simply infinite in that case. So let's do another example. This example is the sum from n is equal to 0 to infinity of n factorial times x plus 1 to the n. This looks something like 1 plus x plus 1 plus 2 times x plus 1 squared, dot dot dot. I think the best way to determine the radius of this is also using the ratio test, because I mean the root test will require us to take the root of n factorial, which we in the limit that's kind of hard to determine. So let's use the ratio test, or sorry, the nth term test. No, I mean, yeah, the ratio test. So the limit as n tends towards infinity of n plus 1 factorial times x plus 1 to the n plus 1 divided by n factorial times x to the n. That simplifies to the limit as n tends towards infinity of n plus 1 times x plus 1. Now, as n tends to a really large value, this essentially goes to infinity, right? Therefore, like no matter what x value we have, our limit blows up. And so there's no value of x besides us exactly making the set, like exactly negating the center where we'll have convergence. And so since this is again a power series, our convergence is now in this case only at one point, and that point is when x is equal to -1, since that will push all the terms to 0. And yeah, because that's the fact that our ratio test shows that for no matter like what value, we'll have this n plus 1 over here, and n tends towards infinity. Finally, let's do one last one. This one says find the summation of n is equal to 1 to infinity of x minus 3 to the power of n divided by 2n. Now, I'll once again use the ratio test. So the limit as n tends towards infinity of x minus 3 to the n plus 1 divided by 2n plus 2 times 2n divided by x minus 3 to the n. That simplifies to the limit as n tends towards infinity of x minus 3 times 2n divided by 2n plus 1. This, as n tends towards infinity, will tend to 1, and then you have x minus 3 left over, so you're simply left with, this simplifies to x minus 3. Now, essentially, the ratio test tells us that we want x minus 3, the absolute value of that to be less than 1. So x minus 3 is less than 1, and 3 minus x is greater than, or 3 minus x is greater than 1. So x is less than 4, and x is greater than, or sorry, yeah. Sorry, this should be, 3 minus x is less than 1. So x is greater than 2. So those are the, that's the interval. And now we have to test the endpoints over here. So when x is equal to 2, we get, so testing endpoints, x is equal to 2, we get this summation from n is equal to 1 to infinity of -1 to the power of n divided by 2n. This is a harmonic series, and so we know that we've seen this before. So this is conditionally convergent. And now we test x is equal to 4 as our second endpoint, and we get the sum from n is equal to 1 to infinity of simply 1 divided by 2n, and this is divergent, which diverges because again it's a harmonic series. And so the endpoint at 4 is not convergent, so our interval of convergence is simply x is less than or greater than or equal to 2 and less than 4. So that's our convergence interval. But our radius doesn't change. Our radius remains 1. So hopefully these examples made solving for interval of convergence easier and finding out the radius of convergence easier. But yeah, it's accumulating all the things that you've learned about not only the different tests but also applying the rules of the theorem of power series and their convergence.